Okay, so if we move on to theme 3, which is all to do with our probability distributions, and that was really the first point in the course where we started to do some real statistics, if you like. Okay, so yeah, that was our probability distributions. Okay, so if you remember, there are 3 distributions that you need to get your head around in this course. Okay, 2 discrete, 1 continuous. Okay, can you give me any of them? So we've already looked at one this morning.
Discrete.
Okay, so binomial is one, Poisson is another. What's the third one? Yeah, good. Okay, so those are the 3, right? These 2 are your discrete distributions. In other words, you can only have specific outcomes within a given interval. Okay, so for example, you're dealing with number of students, well, you clearly can't have half a student, right? Or if you're dealing with the number of tweets in a particular hour, somebody can't give half a tweet in that particular hour if you're using Twitter, right? So these are discrete. This one here is your continuous distribution. So just remember, when you have your probability distributions, right, you need to know how to define them. Okay, so you say, okay, this is my distribution, and you need to be aware of the different parameters for each. So just for binomial, okay, are you happy that if you have a binomial distribution, what are the 2 parameters for a binomial distribution?
Number of samples and
Good. P, what does P represent? Of success, of happening, yeah, okay, that's fine. Yeah, so for binomial distribution, you have a number of trials, a fixed number of trials happening, and you have a probability of success. Now just remember that when you define your random variable for a binomial distribution, it's always the number of successes that you're interested in. Okay, so for example, if you're going up, and I mean, a good example is thinking about somebody scoring goals, right? They're going to have 10 tries at scoring a goal, and the probability of kicking it in the goal, let's say, is 40%. They're not particularly that great. Okay, well then in that case, you've only got 10 goes to get their goals, so you can only have 10 goals as a maximum. Does that make sense?
in 10 trials,
Yep.
The probability of scoring a goal is 40%.
Yep.
Which means
the maximum number of goals that they can score is 10.
In 10 trials,
Yes.
you are scoring 4 goals.
That's what you expect. Good.
Yeah.
That's what you expect. That's the expectation. So you times those two things together, right? So you expect to score 4 goals, okay? But the maximum number of goals that that person can score is 10.
It's 10, because there is 10 trials.
Exactly. So he might, that person, not necessarily he, but they may get every single goal in, right? Equally, the minimum number would be, what would the minimum number of goals that they could score be? 0, right? So basically, if you wanted to find the probability, you would be looking for the number of goals that they scored in that case. Okay? So just remember, with a binomial distribution, it's the number of successful outcomes. Does that make sense? Okay? And it can only be an integer in this case. All right? For a Poisson distribution, we talked about that quite a lot of detail this morning. So that's going to be a Poisson distribution. There's just one parameter. Just remind me, what is that parameter?
Event happening.
Good, the rate of success. Okay, so obviously you need to have a time interval included in this as well. With a normal distribution, what are the 2 parameters?
X variable and Y variable?
No, that's more to do with the random variable. So you basically say X is the weight of a particular chocolate bar, for example, right? Or Y is the height of a student. What are the 2 parameters, though? If you're saying that a random variable is normally distributed, what are the 2 parameters that you need here?
Variance and mean.
Good, okay, and it goes in the reverse order. So mean goes there, and variance goes there. Remember that I said this, I think last week as well, or the week before. The parameter that always goes there in this course is the variance. If you look in other courses or in other books, it may be the standard deviation, but in this course we just use the variance there, okay? Good, and then obviously from this you need to be able to calculate probabilities ultimately. Okay, say, well look, in this particular situation, this is my parameters which I have. Okay, it's normally distributed, binomial distributed, Poisson distributed, whatever the distribution is. Now can you find me the probability that this particular outcome will occur based on this situation? Does that make sense?
Yeah.
Yep. And of course I can ask things like expectation and variance and bits and pieces like that and ask you to do stuff.
I think they are coming in that section now.
What do you mean, sorry?
You said you're not asking in team 1?
Yeah, exactly.
Yeah, you mix.
Exactly, I'm mixing stuff up, absolutely. So it's stuff in here, definitely, yeah. Just be aware as well, I should also point out that there is expectation algebra in this theme as well, okay?
Oh.
So the expectation algebra will be things like, if I take a constant and I want to find the E of A of X. In fact, I'll write it down here. I don't know why I'm writing it in the top right-hand corner. So yeah, expectation algebra.
So you are going to use it, huh?
Yep, could do, maybe. We'll see.
That means we are going to use it.
I don't know. Take what you want from that. Okay. So expectation algebra. You remember that there are 4 different things you need to get your head around. Okay. If I have a constant, let's call it A. And if I want to find the expectation of A times my random variable. So in other words, I take my random variable X and I make it A times bigger. What would that be equal to?
A times expectation of X.
Good, it's just a scalar of the expectation. Excellent, well done. Okay. If I wanted to do the same for variance, okay, so if I took the variance of A times X, what would that be equal to?
Oh, just a moment.
Okay.
Variance of X?
There is still the variance of X in there, but what about the A? Not quite, actually, not in this case.
The way it's...
Yeah, the...
Varyansını etkilemez ki ya. Ve A times? I don't think so.
No,
You're so close.
but very close.
A squared.
Good.
You're good.
Okay, the reason being is because the standard deviation, which is the measure of spread that you generally think about, okay, is going to be times by A. I agree with that. But because the variance is the standard deviation squared, it means that that's also going to be multiplied by A. So really what I want you to think about in your head is that if I have the standard deviation, I'm just going to call it SD for short, of A times X, that's going to be equal to A times the standard deviation of X. But given that the variance is the standard deviation squared, that means that A has also got to be squared as well. That makes sense? Yeah, so think about that, right? That will help you. Of course, there is another way that we can transform our random variable, and that's using an addition. So a translation, if you like. So if I this time add A to every single value in my random variable, okay, what should that be equal to?
Expectation of X.
Plus?
Nothing.
Ooh, not in this case. There will still be a plus A. Okay. Think about it. If I'm saying that I take every single value in my random variable and add A to it, in other words, I'm pushing it to the right by whatever A is, okay, or to the left if it's subtract, it also means that the mean should move with it as well. Does that make sense?
Yeah.
Yeah. What about variance though?
Huh? It is not affecting this.
Good. The A doesn't affect it, right? Just remember, all the plus A does is it literally just picks up wherever your values of your random variable are clustered around at the moment, and just literally picks them up and moves them somewhere else. Okay? So the plus A, if you like, is just adding A to every single value. Variance is a measure of spread. So adding A to all of your values, you're not changing the spread at all. You're just shifting the location of them, right? Whereas here, obviously, when you're multiplying, you are changing the distances between those random variables, right? Because you're timesing them by A. Okay, so you're either making them bigger or smaller. Hence, the spread will also change as well. Okay. So yeah, this one behaves. This one you need to think a little bit more carefully about, but if you think about it, it does make sense. Yeah. So there you go. You've got some expectation algebra in there as well.
We have to know the proofs of this algebra.
Technically, yes, but
Yeah.
no. No, you
Do
don't.
we have to present it in the
No.
paper? Yeah. Okay.
No, absolutely not.
To be honest with you, I think a lot of these are just based around intuition anyway, and that's the way which I presented them to you. Okay, I think I did give you the proofs. I can't honestly remember what is in the notes now. It was a little while ago. But either way, I would not ask you to say, okay, prove that this is true.
Yeah.
Yeah. So just be aware of that. Now, of course, there is also one other thing with probability distributions, which may be that I say, look, I'm going to define a distribution. It's not going to belong to a binomial, Poisson or normal. I'm just going to say, for example, that f of x, let's say my probability mass function for my random variable, may be equal to something like this. So it may be equal to something like k times x squared for x is equal to, let's say, 0 and 1, and it might be 0 otherwise, for example. I could totally do that. Right, that's still a probability distribution. It's basically saying, look, here's my random variable, and this is the outcome of my random variable, and I'm saying the probability of obtaining this random variable is given by some constant times x squared, as long as x is 0 and 1. So for all the outcomes of 0 and 1, we actually have this probability, and it's 0 otherwise, right? So how would I actually figure out what the value of k is? K in this case is just a constant. How could I figure out the value of k?
So basically we need to find k, right?
Yeah, pretty much. It's a constant. I want to find it.
No way.
It's the sum of probabilities.
Good. I know that the sum of all of my probabilities should be equal to 1. Right? So if I literally just stick in x into here, I'm literally saying, well, okay, 0 squared times k, that's just going to be 0, plus 1 squared times k, that's going to be k, has got to add up to 1. Because obviously everything else has a value of 0. Right? So in this case, are you happy that k is just equal to 1? Hence, I just have a distribution like that. That make sense? Right? And then from this, you can work out things like expectation. Right? So if I wanted to find the expectation of my random variable, well, then I can use the true formulas. Remember the formulas in the formula sheet, which was like the sum of x times the probability. Yeah?
Yeah.
And so thus, I could just literally say, well, okay, I have 0 times by 0 squared, effectively, because that's f of x at 0. So that's going to be 0, plus 1 times by 1 squared, that's just going to be 1. So I expect to get a value of 1. Okay, and you could do the same for variance if you wanted to as well. Does that make sense? Right, so I may not necessarily just ask you about the standard distributions. I may also just give you a distribution, okay, and ask you to manipulate that in the relevant way.